Hey, this video is going to go over refraction and Snell's law. Let's get right to it. So refraction is the bending of light as it travels from one medium to another. Medium being like the substance through which light is traveling. In this picture here, we can see that the straw is sitting in a cup of water, but the light you see from the straw in the water is in a different position. The light appears to be bent from that of the straw in the air. It's because the light we're seeing changes directions when it goes into the water. So here's a diagram showing what's happening. The incident ray, which is the incoming light ray, when it transfers from air into water, the light ray gets bent like this. And notice that there's this thing called the normal, which is a perpendicular line to the surface. It's imaginary. It's like not really there, but we, call it the normal line. When going from air into water, the light ray is actually bent, so the incoming angle is greater than the refracted angle. The refracted angle is less, and we measure that with respect to the normal line, not the surface. So this angle's here and this angle's here, both with respect to the normal line, which is that perpendicular line to the surface. So when light moves from air into water, that is from any lower density substance to a higher density substance, the light ray is going to bend toward the normal, as we saw a moment ago. The opposite's true. When it goes from something that's more dense to something that's less dense, it's going to travel away from the normal. And if light went straight down through, like along the normal, so 90 degrees, not at any other angle, then it doesn't get bent at all. The light would just go straight through. Index of refraction is something we're going to need to know for Snell's law and the equation that governs all this stuff, or describes it really well. The index of refraction for any transparent substance is actually like an indirect measure of its density. So the more dense a substance is, the higher its index of refraction, generally speaking. The symbol we're going to use for this is N. This symbol, this quantity, has no units. As we'll see when we solve problems, like all the units would cancel out. And it always has a value greater or equal than 1. So it can't have a value of like 0.5. That would be impossible. That would be like if the light was traveling faster than the speed of light. And we know that to just not be possible. At least there's no evidence that it can. So for example, if light is traveling from a lower density substance up here to a higher density substance down here, like maybe this is glass or something. Think of this as like an enlarged window pane. So light could travel from air into glass and then from glass back into air. Let's see what happens. Other than obnoxious noises. So the light travels, it gets bent when it goes into glass or water. And then when it goes back out the other side, it gets bent again, back to the original orientation. There's another equation that we won't use very much, but it's good to mention. N equals C over V. Remember, C means the speed of light. So index of refraction is the speed of light in a regular situation, which is 3 times 10 to the 8th meters per second, divided by the speed of light of inside that material. So the slower V is, the greater the value of N, which just means that the substance is slowing light down more. So as N increases, the speed of light in that substance decreases, and there's more bending, there's more refraction. The thing we're going to use to calculate all this stuff is Snell's law, which says N1 sine theta 1 equals N2 sine theta 2. Yes, trig functions, exciting. So the 1 stand for the incident light. So the left side of this equation is like the incoming stuff. N1 would be the index of refraction for the first material. Theta 1 would be the incident angle or angle of incidence, which is the angle that the incoming light makes with respect to the normal line. And N2 and sine theta 2 are exactly the same thing, just for the refracted material or the second substance. Here's a chart with a whole bunch of values of different transparent substances through which light can travel. Some of the most important ones that we're going to need: air Notice that the index of refraction for air is extremely close to 1.000293. That's essentially equal to 1. So in problems that we do where light travels through air, we're just going to round that off to 1 for the most part. Also, the highest value one here altogether is diamond. And diamond is special on this list because it's the most dense natural substance. So, or that we know of, on Earth especially. And remember, index of refraction is an indirect way of measuring density. So diamond is the most dense natural substance. It makes sense it would have a higher value on this chart, if not the highest value. All right, so let's go through a couple questions here. In which of the following materials will light travel the slowest? If you said air because it has the lowest index of refraction, you'd be wrong because the answer is actually diamond. The higher the index of refraction, the slower light travels. And that has the highest index of refraction out of all these things. All right, question 2, which of the following is not a possible index of refraction for an unknown material? Hopefully you're looking at these, figuring out the oddball. It's 0.9. You can't have an index of refraction less than 1. It's not possible. It's always got to be equal to or greater than 1. So let's do an example here. Find the angle of refraction for a ray of light that enters a bucket of water from air at an angle of 25 degrees to the normal. So let's start by figuring out what we know. First, we can get theta 1, n1, and n2 from this. Theta 1, the angle of incidence, that's the incoming angle. That's 25 degrees in this example. N1 would be the index of refraction for the first material, which is air in this case. It's starting in air, then going into water. And we can round the index of refraction of air. It's 1.000293. We can just round that down to 1. It's not going to make much of an impact on our answer. Then the index of refraction for water, if you go back to that table and look it up, is 1.333. Then we're going to use Snell's law, n1 sine theta 1 equals n2 sine theta 2. And we're going to solve for theta 2. So let's just... All right, so now we're going to start with Snell's law and plug things in that we know. We know that n1 is 1, theta 1 is 25, n2 is 1.333. So we have all that information right there. Now let's divide both sides by this 1.333 number. So all I did was divide both sides by 1.333. That cancels it on here, so we have sine theta 2 equals sine of 25 divided by 1.333. Because 1 times sine 25 is sine of 25. Type all this stuff in the calculator and get 0.317. It's important to know that we need to be in degree mode for all of these calculations on the calculator. If you need help figuring out how to do that with whatever calculator you're using, just let me know. All right, so to get sine off of the left side, because we're solving for theta, we don't want sine of theta 2. We're going to take the inverse sine of both sides. So that just means you do sine to the negative 1 of 0.317, or arc sine, sometimes it's called, depending on your math teacher. Doesn't matter to me. That's what I'm going to use. Then we type that in the calculator, usually by doing second, then sine in most calculators, or shift, depending on the brand. And we get an answer of 18.5 degrees. It's important you're in degree mode. If you're in radian mode, sometimes you'll end up with like really small decimal answers, and sometimes they'll be negative. That doesn't make sense for what we're doing, so we're always going to use degree mode. We can also use this law of refraction, the idea of Snell's law, to predict where things really are. Like if you're looking down into water, you may have noticed if you've ever reached into a tub of water to pick up something that's in there, ends up the object is not exactly where you thought it was. It ends up in a slightly different position. That's because the light you're seeing from it is bent when it leaves the water. This is refraction in action. All right, so thanks for watching. Let me know if you have any questions. See you.